Good morning, good afternoon, good evening, wherever you're joining from. Welcome to our first webinar of the year. If you guys want to drop us a line in the chat to tell us where you are from, that'd be brilliant. I'll start. I'm from Aberdeen. So my name is Shruti Shivdasan. I'm the chair of the SUT Plus Aberdeen branch. That is it from me. I shall hand over the screen to Bodhi. He shall tell us more about Verlume. So there's been a name change. He can tell us about the company and himself.
Good afternoon, and thank you to everyone for attending this webinar. It's nice to know that there's people located both locally in Scotland, Aberdeen, and also internationally. I'm delighted to share the recent achievements of our small Aberdeen-based company and hopefully encourage a rethink of how energy is managed and distributed in a subsea scenario. I'm a chartered mechanical engineer who has worked on a diverse range of subsea drilling, production, and intervention systems. I joined ECOG, now Verlume, in 2013. Due to the recently announced company name change, I apologize in advance if I accidentally switch between the two company names, but I'll try my hardest to stick with Verlume for this webinar. It was here that I began transferring my subsea skill set to a more renewable-based application with the advent of the Subsea Power Hub. And more recently, the Halo Subsea Storage and Energy Management System. Today, I lead a team that is responsible for the mechanical packaging, and I address qualification requirements when bringing our products to market. Today's agenda will establish context for Verlume's technology, identifying the importance of energy storage and energy management. However, the bulk of the content shall focus on our recent delivery for a world-first application in Hawaii, the AOPS demonstration. The webinar shall conclude with future applications before inviting questions and discussions in a Q&A session. It's a well-known fact that the vast majority of energy required to power an incandescent light bulb is lost as heat as opposed to light. Commercialized during the late 19th century, such light bulbs were common even when I was younger. So this triggered a general worldwide phasing out of incandescent light bulbs in favor of more energy efficient alternatives. Now, I know there are applications where the heat is useful, such as incubators or lava lamps, for example. But in general, this is a classic example of inefficiencies in energy conversion relating to an industrial application. Henry Ford, one of America's greatest industrialists, founder of the Ford Motor Company, pioneered the assembly line, and according to BBC's QI, apparently always drank warm water because he believed the body wasted vital energy warming it up from cold. Now, without attempting to quantify the calories required to raise the temperature of the human body after taking on cold water, this is another interesting view of energy conversion, that the human body expends some of its own energy for something as simple as consuming a cold drink. So on the opposite end of the scale, the latest digest of UK energy statistics reveals that over half of the electricity generated in the UK in 2020 was lost due to conversion, transmission, and distribution. So this is remarkable when you quantify that half of all that available energy being generated doesn't even reach us, the end user. But what all of these examples highlight are the challenges associated with energy conversion. The ability to generate power, distribute it, and then consume it results in inevitable losses, whether that be something simple as switching on a light bulb, or in this case, generating electricity for an entire country. Now, losses may not be eliminated entirely, but they can definitely be improved. And to some extent, this has already been achieved within the past decade. See, when I first joined the business and started reviewing this data back in 2014, that 53% loss value was over 60%. Furthermore, back then, coal remained the dominant source of UK energy, whereas today, whilst renewable sources have increased their foothold in the UK energy mix, natural gas remains the largest source. DNV's Energy Transition Outlook forecasts a pattern of the global energy mix decarbonising, with almost a 50-50 split in 2050 between fossil fuels and renewable energy sources. So this is interesting, right? Because oil and gas is forecasted to be an important source of energy long into any of our lifetimes. But from the examples provided, it is blatantly clear, however, that we collectively need to vastly improve how we distribute that energy, regardless of where it originates. Ask any pool of industry professionals on the most important parameters for delivering energy, and you'll likely be bombarded with a wide range of requirements. Even amongst this very audience, you may hear such phrases as, I want my energy to be secure. I want it to be reliable. Or perhaps, I'm only interested if the energy is clean. Or there might be that one guy who'll say, I'm thinking with my wallet, just give me whatever's cheapest. So this is a hot topic just now, with fuel bills forecasted to rise steeply because of increases in global wholesale prices. The energy trilemma presents a need for energy that is plentiful, can be consumed at an affordable cost, and leaves a green footprint. Now, whilst it is challenging to meet all three requirements, the feat is not impossible. Energy storage and energy management are key enablers to making significant steps towards fulfilling these three criteria. Verlume has a strong pedigree in subsea technology, with many of us having gained experience in the subsea oil and gas industry prior to the business formation. Our first product demonstration, the Subsea Power Hub, coupled a single turbine with energy storage and management, which served as proof of concept that under the right conditions, a system can be entirely self-sufficient with regards to remote subsea operations. The business has since developed its own in-house batteries alongside a subsea battery demonstrator. All of these are precursors to our first commercial Halo, which was recently delivered. When addressing the three stages of how power is delivered from its initial generation, and then distribution, and then finally the consumption, Verlume's expertise lies in the middle category. Industries have gotten really good at harnessing energy across several renewable and non-renewable sources, and we're certainly very good at consuming that energy. It's the stage in the middle where we see our technology emerging. The ability to store energy during peak generation, and then having the intelligence to distribute it during peak demand. By introducing energy management and energy storage into the delivery chain, it reduces energy waste and opens enormous potential to how effectively renewable energy sources can be utilized, particularly for remote marine applications. The Halo combines energy storage with intelligent energy management for seabed deployment. A Halo unit can be coupled to a variety of energy sources, whether it be renewable or even, say, a downline in situ charge umbilical from the vessel. It doesn't matter, as the system is completely agnostic, meaning that it doesn't differentiate between source and end demand, only that it can effectively store energy and provide a stable power output, whether it be for powering a subsea asset, or underwater sensors, or even say diverting that power topside. This is why Verlume's technology can be categorized as a gateway for renewable and clean energy. Now, whilst we've typically focused on community scale applications, the system is scalable to cater for any size of subsea architecture. So you guys have maybe heard in the news recently that Verlume has delivered its first commercial halo for a world first demonstration. The AOPS, or autonomous offshore power system, will verify the 3 stages of power delivery that I explained in the earlier slide. So that's the power generation, the middle stage, the energy storage and management, and then finally the delivery, with several partners responsible for the individual categories. So this is a real world application that doesn't just look at arbitrary power consumption, but a legitimate requirement for energy demand in a remote marine environment. Furthermore, the operations are intended to be fully autonomous, with remote access achievable using 4G and the cloud. The project unites partners from around the world, including the US Department of Energy and the US Navy, whose test site in Hawaii is being used for the demonstration. For the power generation, Sea Power, based in Oregon, has developed its Sea Ray Wave Energy device. The Wave Energy device, or WEC, is then coupled with a Verlume Halo, an energy storage and management system deployed on the seabed. In addition to power and comms, the Halo acts as an anchor for the WEC. And then for the end application, there are a number of partners involved, from demonstrating that the system can power autonomous underwater vehicles via a subsea docking station, to powering underwater sensors for remote monitoring. So yeah, once again, the 3 stages of power delivery can be categorized as generation, distribution, and end application. So here we can visualize, in the context of the AOPS demonstration, how the various project partners contribute to each category. The Halo assembly, as delivered for the AOPS demonstration, has a footprint small enough to be transported via road without incurring abnormal load restrictions, and is designed to fit within a standard 20-foot container for shipping. Its overall mass and dimensions satisfy the seabed stability requirements, but equally the unit is small enough and light enough to be deployed using a small commercial vessel. It has a single input from the WEC via the umbilical, and has up to 7 maximum outputs for distributing power for an end application. The Halo's energy capacity is 51 kilowatt hours, which is similar to an entry-level to mid-sized EV. However, this is capped to control the battery's overall depth of discharge and subsequently prolong its shelf life. Its reserves are intended to be treated conservatively, as opposed to an aggressive power out scenario. Now, just like an EV or the vast majority of modern energy storage devices, the Halo features rechargeable lithium-ion batteries. Although the overall capacity for this model is 51 kilowatt hours, the system can be scaled to include additional storage to any desired size without affecting the core system architecture. The input voltage down from the umbilical ranges from 300 to 370 volts DC. Each of the 7 power outputs is configured for a different application, but combined can achieve a maximum power output of 3 kilowatts. Wireless communications, as well as arming and disarming the individual outputs, can be triggered through the water column and onwards using 4G via Halo's acoustic modem. And depending on the client's operational philosophy, the isolation switch which is ROV operable, may be either switched on surface or on the seabed, but obviously either way, it needs to be switched on before running operations. So when the Halo is in our workshop, we can execute full system testing and communications using a laptop interface. The media converter is necessary for the optical line from the WEC to Halo, which permits wired access. Moreover, using the same laptop interface, we are able to similarly verify wireless transmission with the acoustic modem. So using the onshore charger and assuming that the system is empty, the time to recharge at around 2.8 kilowatts takes approximately 15 hours. Please know that that figure is for a dedicated charger and it's not for an intermittent supply from a WEC or any other renewable source. So obviously we don't have the luxury of a full-scale WEC in our workshop, nor do we have a massive tank that can replicate the Hawaiian test site to demonstrate the full system integration. But we do have the next best thing, a power simulator that's able to replicate measured metocean data into a voltage input. Halo's upper level construction may be split into the frame with removable panels, which are a marine licensing requirement to prevent aquatic life from inadvertently entering the assembly. Once removed, the frame reveals 3 environmental housings secured to a base frame. So within these 3 housings, one is the Intelligent Energy Management System, or IEMS for short. So this is an acronym, IEMS, that I'll be using quite regularly throughout this presentation. The other 2 housings contain the rechargeable batteries. So here it becomes apparent how the system can be scaled by including additional housings to accommodate the extra energy storage, and these can all be subsequently wired back to a central IEMS. So Halo is classed as a portable offshore unit in accordance with DNV 273, which requires a load and impact test. We executed the test at the Jackson Group near Montrose, replicating the full system mass at a 5 by 5 degree angle before releasing the frame. You can see that the sleepers came out worse than the frame, which survived and was subsequently verified using NDT. The environmental housings are sealed in a 1 atmosphere pressure using dry nitrogen as dielectric fluid. To verify external pressure, the system was qualified to 1,000 meter water depth. The housings are constructed from standard scheduled pipe at around 3 meter length, and with both ends capped using machined flanges. We hyperbaric tested at SCOR's facilities in Peterhead. So the term lithium ion has become ubiquitous with energy storage, but its chemistries vary significantly in size, geometry, and characteristics, depending on the end application. So for example, your phone or your tablet may only require a single cell battery that is designed to be robust enough to withstand the frequent mechanical abuse it is likely to take throughout its product life cycle, which realistically might only be, say, every 3 to 5 years to make way for the latest iPhone or Android model. Now, conversely, an EV has an enormous battery pack comprising of several battery cells assembled into modules. Broadly speaking, lithium-ion cells can be categorized as power cells or energy cells, or a combination thereof. A power cell might be used on DIY tools, for example, being able to output, say, 10 to 20 amps without so much tickling the battery. For Halo's application, this is less important to us. The parameter that we are interested in is for the battery to store and hold on to that energy as much as possible until the demand for power is there. this is why energy cells that deliver something like 2.5 to 3.5 amps output is preferable. Moreover, the battery management system, or BMS, which protects the battery from mechanical and electrical abuse, is a prerequisite for a reliable overall parent system. The BMS selected for Halo has a reliable comms protocol, allowing us to accurately receive each individual battery's parameters, such as state of charge or temperature, its charge and discharge status, to paint a picture of the system's overall state of health. The energy distribution between the source, which, okay, for the sake of argument, could be intermittent from the WEC, or it could be continuous from the onshore charger. And any number of end applications is continually being managed by the IEMS, which is able to command individual batteries to either charge, discharge, or simply stay put depending on the relationship between the external power supply and demand. And the charge philosophy is equally important, as the system requires a more even spread of charged and discharged batteries. The IEMS prohibits significant differences in states of charge within the various packs as a means of improving efficiency and reliability. And everything is seamless, right? So the energy coming in might be intermittent from the waves, and the various batteries are in a continual state of charge and discharge, but the system power output for the end application is constant and uninterrupted. So the simplistic illustration only addresses the power distribution, but the IEMS additionally offers a parent level protection for the entire system, addressing parameters such as overcurrent, over voltage, under voltage, over temperature, and under temperature. And the level of protection extends to environmental factors such as gas detection or moisture ingress, because ultimately we're packaging everything to be deployed in a harsh marine environment. In addition to managing Halo's energy storage and power distribution, the IEMS acts as a gateway for renewable power in a remote marine environment. So for the AOPS demonstration, to maximize communication channels to the seabed, there's an optical line within the umbilical connecting the WEC to Halo. So this provides options if personnel are on site and require hardwired access to Halo from the WEC. Otherwise, communications are achieved through the water column. Now, due to the nature of offshore operations, whether it be from a renewable source or even deploying a power line from a vessel, it is possible that the power availability could be inconsistent. Obviously, without intelligence built into a system, a lack of input power could literally mean complete inactivity on the seabed floor. The IEMS actively monitors the input line, and during instances of very low power availability, can autonomously enter into a sleep mode, which keeps the system ticking over rather than drain unnecessary reserves and completely rendering the subsea equipment dead. As soon as there's a nominal charge supply, there is intelligence within the system to run operations as per normal. So although AOPS is a ground-up application, the IEMS is engineered to cater for legacy infrastructure, allowing Halo to be introduced to existing sites to maximize its energy management and distribution. The core technology is adaptable and modular to cater for a wide range of power distribution and subsea communication and pass-through requirements without disrupting the existing site beyond a simple plug-and-play exercise. So before any project, our engineers review the site data to accurately forecast power availability, taking the energy source and end applications into account. So this is a generic example. It's not applicable to AOPS or any other project, but it's been included to illustrate our in-house modeling techniques. The blue line on the top graph represents the power available from the WEC. And as you can see, it follows a variable pattern. And this is to be expected from an ocean resource, because sometimes the waves are good, sometimes it dips slightly. And it's the same approach for tidal. The red line is the forecasted demand. So in this example, between days 30 and 90, that is the AUV requiring the bulk of its power. And then later on, there might be some nominal power requirement for running the underwater sensors. And then take a look at the graph below. You can see, again, from the blue line, that the halo's state of charge takes a hit during instances of peak demand. But that's the point, as the demand is peak instead of continuous. And then similarly, around day 300, due to perhaps, say, a lack of wave power, the halo state of charge starts to dip again before rising from about day 310. So this would be a classic example of the sleep mode operation I explained earlier. Using modeling tools such as these, we can specify a configuration of halo that's required to keep the operations running on the available energy resource and end demand. And it's not just for one arbitrary day, but it's throughout the entire duration of the trial. As you can imagine, when you house a bank of batteries and electronic equipment into an environmental vessel, it is likely to get hot. So temperature analysis is a key influence on the final system configuration. The lower right graph analyzes halo's internal temperatures at various stages of operation. So it looks at, startup through to full functionality. And the analysis particularly assesses how quickly the system reaches these temperatures before dissipating back down again. So when we first started our journey into energy storage and management, we had demonstrated using off-the-shelf components the viability of coupling a single turbine with a subsea battery. To optimize the system, however, and to cater for real-world usage, required the combined skills of electrical, software, and mechanical engineers, as well as expert technicians to design, assemble, and test our first commercial IEMS. It was an interesting experience, carefully running in a 3-meter length of internal circuitry into an 18-inch schedule pipe before adequately securing the internal equipment to withstand the transportation and handling loads. It's a similar running philosophy when inserting the batteries into the environmental housing. Once assembled, the seal integrity is verified with a local pressure test before the housings are purged using dry nitrogen. The system spent several weeks worth of testing during various stages of the build. So here we can see the IEMS opened up and connected to the 2 battery enclosures in the background. It is worth noting that this is an international project with partners located outside the UK and a test site located pretty much on the other side of the world from us, with everybody working under lockdown conditions. Testing was paramount to minimize the operational risks to as low as reasonably possible. So this required studying the full system lifecycle from startup to full charge and discharge. The power simulator used to represent the WEC loads churned out power at enormous magnitudes, all of which were being absorbed and conditioned by Halo's IEMS using its dynamic voltage measurement. So it's one thing to design a system using all of the engineering acumen, best intentions, and theoretical knowledge available. However, the system still needs to be subjected to robust and rigorous testing to provide the confidence that it is fit for purpose. Halo was eventually subjected to a wide range of tests, ending with a wet test of the top-level system. The team verified areas such as the input connection, output connections, both wired and acoustic communications, the ability to remotely function Halo, download and install software, validate the alarms and trips, and validate the sleep mode, etc. So in addition to the WEC, Halo can be charged using an onshore charger, which again offers similar levels of protection as witnessed by the integrated IEMS. The idea being that once Halo reaches the test site, it can be fully topped up prior to deployment and give the project the best possible advantage. So courtesy of the US Navy's Wave Energy Test Site in Hawaii, Halo is destined to be deployed as part of the AOPS project. Its footprint and weight means that a small 85-foot vessel can be used for operations, and this negates the requirement for large specialist boats. So the Halo installation is entirely gravity-based, requiring no additional cementing or anchoring options. In fact, it acts as an anchor itself for the WEC, and its loads were verified in a seabed stability analysis. Once the connections are made and the isolation switch is turned on, then really the plug-and-play system is good to go. Remote access to check system parameters, such as state of charge, arming and disarming individual outputs, and even retrospectively downloading new software onto Halo can all be achieved remotely thanks to a 4G connection and VPN. Now, throughout the sea trial, the underwater sensors shall gather environmental data on whether such a system is disruptive to marine wildlife. The autonomous offshore power system is a world-first demonstration. So this architecture combining the anchor point, the energy storage, the energy management for complete uninterrupted power, it doesn't exist anywhere else. Moreover, the ability for remote access from not just surface, not even onshore, but anywhere with 4G connectivity eliminates the need for personnel to be located on site beyond initial installation and decommissioning. So this is a significant step forward in demonstrating that unpopulated and fully autonomous offshore operations are the future. So on the back of the AOPS demonstration, Verlume is scheduled to deliver a similar system for the Renewables for Subsea Power project, or RSP. A little closer to home this time, we are eyeing up a North Sea deployment for second quarter this year. The project partners include Verlume for the underwater battery storage and energy management system, Motion Energy for the WEC, Harbor Energy for operator support, and with additional support from the Net Zero Technology Center. Furthermore, we're delighted to be working with Baker Hughes, who are providing a SEM that will be integrated to the Halo structure. To simulate what the SEM could power, a DC load bank is being included. An additional power output is included in the form of a nominal 48 volts DC 3 kilowatt connection, which may be suitable for a resident subsea vehicle or underwater sensors, for example. The Halo steelwork offers enormous flexibility in not only scaling the energy storage, but additionally providing mounting locations for external party components. After all, why execute multiple deployment strategies when a single deployment offers simpler, safer, and increased efficiency, particularly if the end application can be mounted directly on Halo itself? As the number of housings increase, then feeding into a common IEMS would require an electrical distribution unit, utilizing an oil-filled compensation system akin to a subsea control module design. Lastly, the key word in adapting for larger energy magnitudes is modularity. Several 40-ton models, each with a gross energy capacity of over 1 megawatt hour, may be deployed and tied back to a central energy management system, effectively resulting in a huge underwater energy storage farm. I hope this webinar paints a picture of the importance of energy storage and intelligent energy management in the context of the wider energy trilemma I presented in an earlier slide. With the wealth of ocean activities in operation around the world, Verlume's Halo technology fits both into legacy architecture to address issues concerning power losses or even unavailability, and future ground-up developments which integrate Halo as a renewable gateway for uninterrupted and fully autonomous operations. Thank you for listening. If anyone wishes to discuss the contents of this webinar or get involved in future Verlume projects, then please get in touch using the new email below or find me on LinkedIn. Otherwise, I now invite any questions.